solar cell or photovoltaic cell actually works. The foundation is silicon. You might know silicon is the second most abundant element in the Earth's crust, right after oxygen. We can find it in sand, rocks, and quartz. But what makes silicon so special for solar cells? It is a semiconductor, which means it doesn't conduct electricity like metals as copper and aluminum, but at the same time, it is also not a complete insulator like rubber. It sits in between, which makes it ideal for controlling electricity. If we go into chemistry, silicon atom has 4 electrons in its outer shell, which allows it to form strong stable bond in a neat crystal structure, which is perfect for creating the core of a solar cell. But there is one issue. Pure silicon isn't enough to generate electricity efficiently. So scientists add other elements to tweak its behavior, and this is called doping. So on one side, they add phosphorus, which has 5 electrons in outer shell. 4 electrons make bond with silicon and 1 electron is left free. So this becomes N-type silicon with full of free moving electrons, which is negatively charged. On the other side, they add boron or aluminum, which only have 3 electrons in their outer shell. That means one bond in the silicon structure is left empty, which creates a hole, a spot that wants an electron. This becomes P-type silicon, full of positively charged holes. Now, when we place the N-type and P-type silicon layers together, then what happens? Free electrons from N side diffuse across the junction to fill holes on the P side. And similarly, a few holes move the other way. As electrons leave the N side, they leave behind positively charged donor ions. And as holes leave the P side, they leave behind negatively charged acceptor ions. These ions are fixed in the silicon lattice, they don't move. This results formation of depletion zone, or we call it PN junction, because there are no free charge carriers, means no free electrons or holes left in this zone. So now near the junction, N side will have positive fixed charges and P side will have negative fixed charges. Anytime you have a separation of positive and negative charges, nature creates an electric field between them. And this electric field points from positive N side to negative P side. And it acts like an invisible barrier or voltage difference across the junction. And it tries to push electrons back to the N side and holes back to the P side. Once the PN junction is already formed and stable, the cell is ready to generate electricity from sunlight. Now when sunlight hits the solar cell, this is where the real photoelectric magic happens. Sunlight is made of photons, which are tiny packets of energy. The more energy it has, the more impact it can make. These photons hit the top surface of the solar panel, which is the N-type silicon layer. This layer is made thin and slightly transparent so that photons can pass through to reach the depletion zone and P-type layer below. Now if a photon has enough energy, at least 1.1 electrovolt, which is the energy band gap of silicon, it hits a silicon atom and does 3 things. It breaks a bond between atoms. These are covalent bonds. It kicks out an electron and sends it into the conduction band where it is free to move, and it leaves behind a hole. This creates what is called an electron-hole pair, a free moving electron with negative charge and a hole with positive charge. Here, where the depletion region becomes powerful, the internal electric field inside the depletion zone acts like a separator or gate. It immediately pushes electrons toward the N side, the top layer, and pushes holes toward the P side, the bottom layer. This separation prevents recombination and builds up voltage inside the solar cell. Now imagine we connect an external wire from the top N contact to the bottom P contact. So the electrons now at the N side are eager to return to the holes at the P side. But they must travel through the external circuit, the wire. And while doing that, they will do extra work. They can light a bulb, they can charge your phone, and they can run your fan. So this flow of electrons is called the direct current, DC, the kind of electricity solar panels produce. As long as sunlight is hitting the cell, new electron hole pairs keep getting created. The electric field keeps separating them and electrons keep flowing through the wire. And that is how solar panel turns sunlight into usable electricity. Here is one more thing. A single solar cell only produces about 0.5 volt. So that's not enough to run anything meaningful. So what we do, we connect 60 to 72 cells in series to make a solar panel, which gives around 30 to 40 volt. To power homes, we then combine multiple panels into a solar array that can produce 1 kilowatt, 5 kilowatt, 10 kilowatt or even more. How is solar panel built? Think of a solar panel like a solar sandwich. It is made of multiple layers, each with a special job. The top layer is glass layer. This is a tough transparent glass that protects the panel from rain, wind and even hailstorm. It is the first layer sunlight hits. Second layer is anti-reflective coating, ARC. This is a special coating layer just below the glass layer. Why? Because we don't want sunlight bouncing off. This layer helps trap more light inside. The third layer is encapsulant layer, top EVA. This layer works like glue. It holds the delicate solar cells in place and protects them from dust and moisture. Fourth one is the main layer, solar cells. Here is where the magic happens. These silicon cells convert sunlight into electricity. A single cell makes about 0.5 volts and multiple cells are wired together in the panel. The fifth layer is again encapsulant layer, bottom EVA. It is another sticky protective layer, like the bottom slice of bread in our sandwich. It cushions and protects the cells. Sixth layer is backsheet. This is the back cover of the panel, usually in white color. It provides insulations and shields the panel from weather. Seventh and last layer is junction box. This is where all the electrical wiring from the cells comes together. It lets you connect the panel to the inverter and your home system. So in total, there are 6 to 7 layers, all working together to turn sunlight into clean, usable electricity. Now let's explore the different types of solar panels available and understand how they differ in design, performance and application. The first type is called monocrystalline solar panels. These are made from a single pure crystal of silicon. Because of this, they look dark black and work really well. They can turn about 18% to 22% of sunlight into electricity. They are a great choice if you don't have much space, but at the same time, they are also more expensive. You can recognize these panels by the round edges on the cells because they are cut out of round silicon rods. The second type is polycrystalline solar panels. These are made by melting pieces of silicon together. They look blue and have a kind of shiny patchy pattern. Their efficiency is a bit lower, around 15 to 17%, but they are cheaper and easier to make. The cells in these panels have square edges, which helps reduce waste during manufacturing. Then we have thin film solar panels. These are made by putting a very thin layer of special solar material on surfaces like glass, plastic or metal. They are much lighter and more flexible than the usual panels. Their efficiency is lower, about 10% to 12%, but they do better in shady or low light areas. The downside is that they don't last as long and can lose performance over time. The last type is bifacial solar panels. These are smart panels that can catch sunlight from both the front and the back. They are usually made with monocrystalline cells. The backside collects sunlight that bounces off the ground or roof, especially if the surface is white or shiny. Because of this, they can produce 5% to 30% more electricity than normal panels, and it all depends on how and where they are installed.